finally getting to a lesson I should have done a long time ago on the expanded octet. And no doubt you guys are all going to be really happy about this and really positive and say, geez, thanks, Mr. Orlando, finally getting this. So this was the last reach ahead from Unit 1, conveniently coming right at the end of Unit 2. And this is on the idea of the expanded octet. And in your 1.5 assignment, you saw a case of an incomplete octet. And that was where the central atom of a molecule didn't have its full 8 electrons to have a full shell. Today we're going to look at the opposite case. We're going to look at a case where the central atom of a molecule actually has more than 8 electrons. And we call this the expanded octet. And the first question we want to ask is, how do we know this is even possible? And the answer is because these are all just models that explain things. And we've observed it. We know that the compound PCl5 exists. So phosphorus pentachloride. And so if we take a minute and we draw a Lewis diagram of this, we'll see what the issue is here. So phosphorus, like nitrogen, gives us 5 electrons in its valence shell. And then chlorine gives us 7. And of course, we've got 5 of them. So that's going to give us a total of 35. And this gives us 40 electrons with which to make this compound. So we're going to follow the usual rules. The least electronegative will go in the center. And in this case, that's a phosphorus. And then we're just going to put around it the chlorines. And we're going to connect them all with a single bond, just like that. And then we're going to go ahead and complete the octet of every surrounding atom. In this case, that's all of the surrounding chlorines. All right, and then we're going to quickly count electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So that gives us 40 electrons, which is the right amount. So this is the correct structure. But I hope you'll see that we do have a problem in that phosphorus now has 10 electrons in its valence shell. I guess this calls for a highlighter, really. So at this point, there are 10 electrons in phosphorus's valence shell, which we know should break the rules. But this is only possible because phosphorus is able to form hybrid orbitals using not only its s and p orbitals, but its empty 3d orbital as well. So in its ground state, keep in mind that phosphorus is supposed to have 5 electrons in its outer shell. And so that'd be 1, 2, 3, 4, 5. And we would normally expect this to make sp3 hybrid orbitals. But what happens is that this electron here is actually going to get promoted to the empty 3d shell. All right, and so we end up with 1 electron in 3s, one electron in each of the 3p's, and 1 electron in 3d. And once this happens, these can form a hybrid orbital. And what we end up with is a 3sd orbital. And this tells us that it's an orbital made from the 3s, all 3 of the 3p's, and then 1 of the 3ds. And once this happens, of course, phosphorus is ready to make 5 sigma bonds, because each of those orbitals has 1 electron in it, which means each of those can make a sigma bond. And that is indeed exactly what we find here. We have phosphorus making 1, 2, 3, 4, 5 single bonds. So by this method, by promoting an electron to the d orbital, we can end up with more electrons in the valence than just 8. But really quickly, we need to note that the electrons have to be able to go somewhere. So for example, if we try to make nitrogen pentachloride, NCl5, we should get the exact same thing. We should get N gives us 5, the 5 Cl's give us 35 for a total of 40, and we would get nitrogen in the middle, and chlorine like this. Yep. Yeah. Can you give me just a minute? And we can fill it out, and we can count, and it all works, and we get the full valence shell. There's just one problem. This doesn't exist. This structure isn't real. We don't find it. Why don't we find it? Because N is in the N equals 2 valence, and that doesn't have a d orbital. So NCl5 doesn't exist because the way that this happens is, remember, that 3s electron gets promoted to the 3d shell. Well, there's no such thing as a 2d shell, so there's no way to promote an electron to a d orbital and give us this sp3d. 5 does exist, but NCl5 doesn't exist. And the simple rule of thumb for this then is that only atoms in the third shell or beyond, only atoms where N is greater than or equal to 3 are able to find hybrid orbitals. Sulfur should give us 6 electrons in its outer shell, and 4 oxygens should give us 24. And the 2- charge should give us 2, and that gives us a total of 32 electrons. And if you follow all of our regular rules, you'll get this structure, the sulfate ion, all right, with sulfur in the middle and single bonds to each of the oxygens. The problem with that is, if you look at the sulfur, it ends up with a formal charge in this case. And if we calculate it, we know that sulfur starts with 6 valence electrons, and that we have to subtract 1 for each bond it's making. And so in this case, sulfur is making bonds. And we have to subtract the number of electrons around it, and there aren't any, so we subtract 0 there, and we end up with +2 as a formal charge. Which we can tell intuitively just looking, because sulfur is making 2 more bonds than it should. Which that doesn't immediately tell us that's the number, but it's a good hint. And in this case, each oxygen has -1 formal charge. And again, the hint for us there is that each of them is only making 1 bond, when normally they make 2. So 1 fewer bonds. Now the thing to keep in mind is that this isn't allowed. You're not allowed +2 formal charge. That breaks the rules. If we make this same structure and then bonds, well, not and if we do that, we can quickly count and see that we have 2, 4, 6, 8, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons, just like we should. And now, if we look at formal charges, oxygen's got its exactly normal electron configuration here, 2 lone pairs and 2 bonds. So that's a formal charge of 2. This oxygen, again, has 2 lone pairs and 2 bonds, so it's a 2. This oxygen is only making 1 bond, so it's going to be a -1 formal charge. This will be a -1 formal charge. But then if we look at the central sulfur, it's 6 minus, so we take its valence and we subtract 1 for each bond it's making. It's making 1, 2, 3, 4, 5, 6 bonds. And we subtract all the lone electrons around it, and there aren't any. And so we see it has a formal charge of 0. And so in this case, this structure is good. And of course, resonance tells us that the double bond could be anywhere. So if we look, the resonance structures are actually 6 equally likely structures with the double bonds next to each other this way, or next to each other that way, or across from each other, or across from each other this way, or next to each other this way, or next to each other that way. So 6 possibilities. But again, the basic idea being the double bond is necessary not to satisfy the octet rule, but to make sure formal charges work. But if you look, sulfur now has an expanded octet. For this to happen, sulfur has to use 2 d orbitals to give it a total of 1, 2, 3, 4, 5, 6 hybrid orbitals. All right, each of them making a bond. All right, and just something to keep in mind, that because 2 of these are pi bonds, 2 of them actually stay in d orbitals. They don't actually hybridize. And the last example I want to talk about is that there can be lone pairs. So if we looked at iodine tetrachloride, well, iodine gives us 7 electrons. Chlorine also gives us 7, and there's 4 of them. So that's for a total of 28. And it has a -1 charge for a total of 36 electrons. All right, and this is a strange structure, but if we look and follow all of our regular rules, we put the least electronegative in the center, and that's iodine. I'm going to make it a little smaller so we fit. And then around it, we put the chlorines. All right, and we know that the whole thing is going to have a -1 charge. And so we make single bonds between them. And then we fill the surrounding valences just like that. All right, and then we count electrons. And we'd say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Only 32 electrons. And that should tell me that I need 4 more. And of course, there's only one place we can put those, and that's on the central iodine. And so keep in mind, since that's the only place we can put them, we have to put them there. But when we do that, we see that iodine has 12 electrons. Well, this is possible because iodine can have an expanded octet. So again, to do that, we have to have 12 orbitals in iodine's valence shell. And how that works is an sp3d2 hybrid orbital. All right, and specifically for iodine, that's in the 5th shell. So it's a 5sp3d2. And we get 1 of those from the S, 3 from the P, and 2 from the D, for a total of 1, 2, 3, 4, 5, 6 orbitals. And if we look here, we see that it has 2 lone pairs, and it's making 4 sigma bonds, just like that. So that would be its electron configuration. And last thing to keep in mind is, of course, that these also have a shape. So we can have an sp3d, or we can have an sp3d2. And both of these have different shapes. So if we look here, in this case, if they're all filled by a bond, we have a triangle that makes up one plane, and it goes up along 2 ways. So this ends up looking like 2 pyramids stacked on top of one another. There's one pyramid shown in blue, and then on the bottom, we have a pyramid shown in red. All right, and we call that trigonal pyramidal. All right, so if we had sp3d with everything making a bond, we would call that trigonal pyramidal. And this is an example of that. All right, sp3d, they're all making a bond. So phosphorus pentachloride is trigonal pyramidal. But we can also have a shape that we call seesaw shaped. And if you look here, this is like a straight line. It's got two lines coming off of it. And that's if you have the same hybridization, but it has a lone pair of electrons. We get a T-shaped molecule when we have two lone pairs of electrons. And of course, we get something linear when we have three pairs of electrons. All right? And that's what happens when you hybridize with an s orbital, three p orbitals, and a single lone d orbital. Of course, we can also have sp3d2, and in that case, we get a shape called an octahedron. It's kind of like two square-based pyramids. Or we get a square-based pyramid if it has one lone pair of electrons, just like that. Or we actually get a perfectly flat square if it has two lone pairs of electrons. And after that, you would get another T-shaped and then bent and then linear, but we don't need to show that. So you're not expected to memorize these shapes, not at this level, though later on you will be, but just to give you a sense that these indeed also have unique molecular geometries. So I hope that helped. I'm adding some questions now. Thanks for watching.